Hi, thank you for joining this talk. Today I'm going to talk about our research on students' teamwork on programming projects and what we can learn from their GitHub logs. First of all, why do we want to study students' teamwork? Teamwork is central to professional programming and is getting more and more involved in college introductory courses. Working in teams enables students to work on larger scale projects than they would individually and to learn from their peers and also prepare for their future jobs. While working in teams, students use several online tools such as GitHub and SVN, which provide the researchers with a lot of logs on the students' interactions. Using these logs, we can analyze and understand what kind of teams support students best at improving and learning during the course. Social learning theory suggests that for the students to learn in a social environment, they need attention, reproduction, retention, and motivation. Prior research also suggests that when all the team members are engaged in a project, it leads to better learning and performance for the students. They also usually define teamwork quality as communication, coordination, balance of contribution, mutual support, effort, and cohesion. As we can see, most of these qualities are very qualitative and very hard to quantify. To measure the teamwork quality of the students, there are several ways that are suggested before. The first way is using student surveys, which is often based on peer evaluations and are often hard to rely on for grading the students. The second way is using supervisor assessments, which are usually qualitative evaluations, difficult to quantify, and take a lot of time from the supervisors. More recently, several tools are offering different measures to the supervisors to take into account when making those evaluations. These tools still need the supervisors to address all these measures and decide on the evaluation, and they're not fully automated. There are two different types of collaboration that are often observed in software development projects. The first type, or having collaboration, means that the teammates are working towards the same goal. The second type, or working cooperatively, means that the teammates are working towards different goals, but they're supporting each other in reaching their goals. Our observation on the students working in projects showed us that some of the students work on the same parts of the project together. So for example, they worked on implementing a feature together. We called those teams collaborative workers. There are also some teams that work on different parts of the project and they split the work by different parts of the project. So for example, one of the team members does writing test cases, the other one does documentation. We define those as cooperative workers. And we also noticed that there are some teams that only one member made most of the submissions. We called those teams solo submit. I need to mention that those teams are not necessarily solo work teams because it's possible that the students both worked on the project and shared the code base offline and not on GitHub. In this work, we aim to automatically identify the teams with weaker teamwork styles. To do that, we define two different hypotheses. The first hypothesis is that we can automatically classify the commit messages of the students into the different parts of the project. And as I will discuss in more details later, these parts of the project are the parts that the students are often graded on. So for example, implementation, testing, bug fixing. In the second hypothesis, we want to automatically classify student teams into being collaborative, cooperative, or solo submit. To address these hypotheses, we gathered the dataset of two offerings of Java Programming Concepts, or CSE 216 class offered at NC State. This class had two midterms, one final exam, and three programming projects. The first programming project was done individually, the second project was optional pairs, and the third project was mandatory pairs. For both team projects, the students had to do a first design part individually, and if they failed to do that, they were not able to work in a team for the second part. The students in these classes used GitHub for submitting their code and keeping track of their code, and also for sharing a code base with their teammates. Their GitHub repositories were connected to a Jenkins server, which ran the teaching staff test cases on their submission every time they submitted their code, so they were able to get immediate feedback. This table shows some of the statistics of these classes. We can see that both of these classes have around 200 students. They have 9 teaching staffs, and both of these classes have a distance education section, but we focused on the on-campus section, which had 2 and 1 instructors accordingly. And both of these classes have an average grade of around 79. To address our hypotheses, first of all, we defined 7 categories of commit messages. These categories were the parts of the project that the students needed to do and were graded on mostly. So for example, implementation addressed implementing a new feature. Writing test cases was defined because the students were graded based on having enough coverage in their code. The students are also graded on having a specific style, which was measured by specific Eclipse add-ons such as CMD. The students were also they also needed to have Java doc on their code, which is one of the categories that we have defined here. There were also merge commits, and anything that didn't belong in any of these categories went into the other category. So to do the classification, we first manually labeled 400 commit messages into one of these categories. After that, we used the cascade model to automatically classify the labeled commits using 5-fold cross-validation. Then we used the trained classifiers to label the remaining commit messages, which were about 30K in total. This is an overview of our cascade classifier. For the first 4 parts, merge, documentation, style, and other, we used static keyword matching to find the commits that belonged in these categories. We observed that most of these categories were easy to find using keywords. So for example, merge commits usually were auto-generated and included the word merge. Documentation commits often mentioned Java doc in them. Style commits usually mentioned the style tool that that kind of fix belonged to. And we also noticed that other type of commits usually didn't have any meaningful English word in them. So we used English corpus to identify the commits that didn't have any meaningful word and identify those as other. After that, anything that was remaining from these classifiers was passed to the other classifiers to identify implementation, bug fix, and test case type of commits using TF-IDF features and logistic regression. After that, anything that was remaining from all these classifiers again was added to the other type of commits. This table shows the distribution of different types of commits and an example of each of these. We can see that most of the student commits were implementation and bug fixes. For the second part, we wanted to automatically classify student teams into collaborative, cooperative, or solo submit. We had a total of 248 teams, and we asked 2 subject matter experts, which were both graduate students at NC State who had TA'd for several courses before, to manually label 20 shared repositories. They reached a Kappa agreement of 0.88, and then they labeled the remaining repositories separately. So they labeled a total of 100 teams into one of these categories. We then defined some features based on the students' activities on different parts of the project and used those features to automatically predict the students' teamwork labels. After that, we used the trained models to label the remaining of the teams. The features that we defined based on student activities are shown here. All of these features were defined for each of the users and each of the category of commits. So for example, we defined the total number of commits for user 1 and user 2, and the total number of implementation commits for both of them, and also the total number of testing commits for both of them. So we defined the total number and the percentage of commits. We defined the total number, the percentage, and the average per commit of additions, deletions, files changed, and the amount of change. We also looked at the total and average length of commit messages, the total number of pair programming commits, which were identified by mentioning the word pair program or double P by the students in the commit message. We also looked into the prior individual performance of the users and the risk label, which was suggested by the instructors as having a grade less than 60. We also looked into the team selection method as selecting their teammates or being assigned to the team by the instructor. We used random forest feature selection and recursive feature elimination to find the most effective features, and then we use random forest and logistic regression and 5-fold cross-validation to identify the teamwork style of the students. Having a look at our results, we can see that static keyword matching was pretty successful at predicting merge, style, documentation, and other kind of commits. We can see that we were able to reach an F1 score of 0.95 or above. After that, we can see that using logistic regression and TF-IDF features, we were able to achieve an F1 score of 0.84 or above for implementation, bug fix, and tests. After that, anything that was left from all these categories and wasn't classified by any of the classifiers, again, was added to the other category, which we can see that it brought the precision of this category lower. Having a look at the distribution of different commit types, we can see that implementation and bug fixes were the most common type of commits by the students. Something interesting is that the other kind of commits was more common in 2015 and became less common in 2016, which is because that the instructors started grading students on having meaningful commit messages in 2016, and we can see that it was reflected in the number of meaningless commits by the students. Trying to automatically classify student teams and their teamwork style, we can see that Random Forest was pretty successful and we were able to achieve an F1 score of 0.68 or above. And we can see that identifying solo submitting teams was easier than the others, and we were able to achieve an F1 score of 0.9 for this class. Looking at the distribution of different teamwork styles, we can see that most of the students worked collaboratively in these classes. And we can also see that 44 repositories were not able to be classified by our classifiers, which we will try to improve our classifiers in the future to address this issue. As a conclusion, we automatically identified student activities on different parts of the project based on the text of their commit messages. We then automatically identified students' teamwork style in projects based on their online activities. I need to mention that the students were not graded for their amount of contributions to the project, so they were free to share the work any way they wanted. This is why we believe that the work in this research is able to be generalized to different classes. The findings of this research in the future can help us analyze which styles of teamwork lead to better performance and can help us design adaptive support platforms for the instructors. In the future, we plan to compare the performance of students in different groups. We plan to use semi-supervised learning for commit message type and teamwork style classifications to improve their accuracy. And we plan to study students' teamwork using other measures such as selecting teammates, having similar study habits, or having close performance. This work was supported by NSF, and I'll be taking any questions. Thank you.